Hello, everyone. Today's topic is transformations of functions. And this is a very important section for you to be comfortable with because rather than the elementary, simplistic, and time-consuming technique of graphing functions by plotting points, it's so much better if you'll just have some basic understanding of 8 base functions and know what their graphs look like, and then know what transformations of those graphs look like. We'll be transforming horizontally, vertically, shifting left and right, shifting up and down. We'll be vertically stretching by multiplying a function by some value, vertically shrinking, and then also horizontally shrinking and stretching, and then also reflecting about the x-axis and the y-axis. We need to know how every one of those is going to affect the function of the graph, and then more importantly, the graph of what it is going to turn out to be. Now, first step here, recognizing graphs of common functions. So we're going to go through some 8 base common functions that you should be familiar with. Hopefully you look at them all and say, well, yeah, of course. Use vertical shifts to graph functions, use horizontal shifts to graph functions. Like I said earlier, we'll also be using reflections, vertical stretching and shrinking, and then horizontal stretching and shrinking. And then we'll be able to graph functions that involve all of these within them. The only thing that you need to remember whenever you're graphing a function that's going through several different transformations is that you always need to do any horizontal transformation first, and then you always need to do any vertical transformation last. So vertical shifts come last, horizontal shifts comes first. As far as stretching, shrinking, reflect, doesn't matter the order. We'll talk about that more when we get towards a problem that does all of that. First up here, I want you to be very, very, very familiar, if you're not already, with the graphs of a constant function. If I say f of x is just equal to some number c, like that could be y equals 5, y equals 3, y equals 2. We know it's just a horizontal line. F of x is equal to x. That's just our slope-intercept equation. That's a line going through the origin with a slope of 1. And then absolute value of x, absolutely important to know that that looks like a v function. X squared looks like a u function with its vertex on the origin. The square root of x looks like a half parabola turned on its side starting at the origin. X cubed, we should be familiar with that. I always think of it as it kind of looks like at least one part of an x, except it flattens out through the origin. We'll be talking about that. And then the cube root of x, it's just the inverse of x cubed. So instead of going up quickly, it's going to go up slowly. It kind of looks like the square root of x for positive values, but then it's also defined for negative values. We'll look at all of those graphs. First up, our constant function. So if I say f of x is equal to any number c, you just say, well, all I need to do is draw a horizontal line at that particular value of c. The function I have drawn here would be f of x is equal to 1.5. It's halfway in between 1 and 2, so it's a y value of 1.5. And we know that they go on and on forever. Its domain is from negative infinity to infinity. The range, though, would just be whatever the value that c is, and it never gets away from that. Now, if I talk about odd functions in which I have f of x is equal to x, I can say, well, yeah, clearly it is an odd function because it's symmetric with respect to the origin. But then what I also need to know about it is I kind of think of it as having a starting point at 0, 0, the y-intercept and the x-intercept, and then it's going up with a slope of 1 over 1. It goes up 1 over 1. So that gives me a good starting point if I want to graph any transformation of that function. So if like if I said, well, what would the graph of 2x look like? You say, well, it's just going to have a slope of 2. It's going to go up twice as fast as this graph would. So you'd say go up 2 over 1, and you'd connect those 2 points in. It'd be pretty easy to do. Now, on the other hand, if I have something looks like an absolute value, just say, again, that just looks like a v function where the base of the v is on our origin. It's the same thing as y equals x, except for these values in which y equals x would be negative, the absolute value is forcing them to be positive. And so I need you to remember that base graph, because we will be taking transformations of that. And if you don't know what the base graph of y equals the absolute value of x looks like, then you're not going to be able to use the transformations. Up next, like I said, are y equals x squared. It's just a parabola with its vertex on the origin at 0, 0. And you can see we know it's decreasing from negative infinity to 0, and it's going to be increasing from 0 to infinity. Now, as far as the next type of function, square root functions, very important as well. Just like with the parabola, I think of that as having a starting point on the vertex 0, 0, and it going up to the right and up to the left. With this, I think of it as having a starting point at 0, 0, but it doesn't exist to the left of 0, unlike y equals x squared. You can only have positive values of x or 0 inside the square root. That's why I say its domain is from 0 to infinity. But now that range, even though the range is also 0 to infinity, it goes to infinity much slower, because that y value is always going to be the square root of whatever the x value is. So it almost sort of flattens off, but it's never going to exactly flatten off. It just gets less and less steep, but it's going to keep on going up and up and up and up forever and ever. So it will eventually get to infinity. Now, that's why I'm saying the function is increasing from 0 to infinity. It's always going to have a positive slope. It's always going to be going up and up. But again, I just need you to remember the basic shape, because we're going to be transforming that function. Think about what this would look like if I multiplied all of the y values by 2. What if I shifted it 2 units to the right? What if I shifted it 2 units to the left? What about 2 units down? We're going to be looking at all of those different iterations of each of these graphs. For the next one here, y equals x cubed, I just need you to remember, again, the domain is all real numbers, just like y equals x squared was. Now, the right-hand side of this almost looks like y equals x squared. It flattens off and then it starts growing quickly. The left-hand side, very different, because unlike y equals x squared, which is going to form a u up here, y equals x cubed, when x is negative, the y value is also negative, because a negative value cubed is a negative. So points I usually use here to define these, instead of the ordered pair 1, 1, usually I use 2, 8 and -2, -8 in order to plot out a couple of points. And it does have the starting point of 0, 0, goes up to the right of that, down to the left of that. The cube root of x, again, I think of 0, 0 as the starting point, but unlike y equals x cubed that increases rapidly as x increases, the y value here is going to increase slowly as x increases. The right-hand side of this graph looks very similar to the square root function. It actually grows even slower than the square root function, since it's the cube root function. The square root function would be up a little bit above this. Now, off to the left, it's just the same thing. It's an odd function. It's symmetric with respect to the origin. What you see in quadrant 1 has its equal and opposite representation in quadrant 2. Just some points to help you out here. If I were thinking, what x value do I need to get to before the y value gets to 2? And you'd say, wow, okay, I'd have to say the cube root of 8, since 2 cubed is 8, the cube root of 8 is 2. That shows you how much this graph flattens out. It's not going to get to a y value of 2 until x gets way over to 8. That'd be beyond where my screen can handle. Similarly over here, it's not going to get to a y value of -2 until the x value would be -8. You can see here that the x value of -8 would probably be way out about right here. And that's just for the y value to go down to a y value of -2. So that shows you how much this is going to flatten off quickly. But even with that, it still has an infinite range that's going to go from -infinity to infinity. Now, when we start thinking about the transformations we can do to these common graphs. So the common graphs you must know, the constant function, the linear function, the square function, the absolute value function, the cube root function, and the x cubed function, and I'm missing one. Well, I've shown them all, whether I mentioned them all or not. I'm missing one. It's bugging me which one I'm missing, but we'll see that through here in the examples. The graph of f of x plus c. So what if you have some function, you say, I'm going to add some constant to it? Well, that's very easy. You've just vertically shifted it upward c units. So you need to remember, when you add c outside of what's happening to x inside of a function, it's just going to shift it up c units vertically upward. Similarly, if you subtract c, it's going to shift the function down c units. To see an example of that, notice what I have here. I have f of x is equal to the absolute value of x, and then I say, well, okay, what's the difference of that and the graph of g of x, which is the absolute value of x plus 3? Now, don't be misled by these graphs. Sometimes people will think, well, your red graph is smaller than your blue graph. That's just the way it has to appear to fit them both on the same graphing period. They are the exact same shape. Well, what's the difference in them, though? Well, the blue graph is just your basic absolute value of x function. As x goes from 0 to 10, the y value goes from 0 to 10. As x goes from 0 to negative 10, the y value cannot become negative. It has to stay from 0 to positive 10, since the absolute value of negative 10 is 10. Now, what happens to my graph of g of x? Well, it's going to take all of those values of f of x and just say it's the exact same square root of x function, but I'm just adding 3 to the y value everywhere. So now what I will always want you to do anytime you're trying to show me how one graph is changing to another graph is I want you to at least plot 2 points out on each graph and show how those, or 2 points out on the original graph and show how it transformed to the other graph. Now I actually did, well, 3 on my original graph, and you can see the 3 corresponding points on the ending graph, even though I didn't label the middle point here. But please notice here, on your original graph, you had the point 0, 0. Well, okay, that's being shifted up 3. That's why you have the ordered pair 0, 3 on the absolute value of x plus 3. Your original graph, oh, and I didn't plot it here, but your original graph would have the point 2, 2. Well, its shifted graph has the ordered pair 2, 5. It shifted up 3 units. Now, I didn't show what happened to the point 4, 4 when it shifted it up, but it would obviously be 4, 7. Now, on the homework, whenever I did these problems, I tried to show points on the original graph, and I always showed how those points transformed throughout the problem. So you can see precisely what happened to individual points. And I think that's a little bit more effective than just showing random points on each of the graphs. But in this case, all I'm needing you to understand is that, well, it's just the original graph shifted up 3. No big deal. Now, horizontal shifts, and a lot of times students get horizontal and vertical shifts confused. And what I need you to see is that vertical shifts occur whenever whatever is happening to x does not happen to that number. So you say, well, x is inside of an absolute value. Well, is that plus 3 inside of an absolute value? Of course not. That's why it's a vertical shift up 3 units. Now, on the other hand, I say, well, what if you have f of x plus c? So whatever is happening to x inside the function happens to c. Well, in that case, it's a horizontal shift. And horizontal shifts, and I'll just go ahead and tell you, anytime something is in with the x, it does the opposite of what the sign implies. You would think, hey, plus would imply, even if I tell you that's a horizontal shift, you think, well, doesn't that mean it goes to the right? Nope, it's the opposite. Anytime it's in with the x, it's the opposite of what you would think. So you just need to remember, well, plus c when it's in with the x, that's going to be a horizontal shift left c units. So when I say f of x plus c, that's shifting left c units. F of x minus c is going to be shifting c units to the right. You would think minus c, hey, shouldn't I be shifting to the left? No, it's the opposite of what the sign implies. So we'll shift those c units to the right. Now, in order for you to see that, you have the absolute value of x. Okay. Now, I'm saying g of x is that same absolute value of x, but now it's going to be the absolute value of x minus 4 inside of that. And so automatically, you should understand that this minus 4 is not a vertical shift because it's in with the x. Okay, anytime something is in with the x, it's a horizontal shift, and horizontal shifts, you do the opposite of what the sign implies. So I need to understand, okay, g of x is just the graph of f of x shifted 4 units to the right. That's why I say here, solution, the graph of g of x is just going to be shifted 4 units to the right. So I graphed out my basic square root function, and then I showed, well, my g of x is going to be shifted 4 units to the right. So the point 0, 0, my starting point for the square root function, becomes the point 4, 0 on the graph of g of x, its starting point. And then I would need to show every single point on that graph is shifted 4 units to the right. So please notice here where I say the ordered pair 4, 2, it shifts over and becomes the ordered pair 8, 2. And again, it's just an optical illusion when you're thinking, well, that red graph is smaller than the blue graph. It's not. It's just I'm not able to graph the whole thing on the same graphing screen. It automatically is cutting off all but it goes up to about that portion of the original curve because I can't go past that on the same screen. So same size, it's just shifted 4 units to the right. Now, when I'm talking about reflections, if I want to reflect about the x-axis, I need you to remember if you're reflecting about the x-axis, you're changing the sign on the y. Positive y is above the x-axis, negative y is below the x-axis. So I can say, okay, well, if I'm changing the sign on y, remember, f of x is the same thing as y. So if you change the sign of out in front of your entire function, so like if it's a square root function, if I put a minus out in front of the whole square root, the square root's going to be reflected about the x-axis and it would be going down. In the last problem, if I would have said, what does the negative square root of x look like? I would go in here and say, well, it still starts at 0, 0, but then instead of going up, it would go down and it would contain the point 4, negative 2 down here, and it would keep on going on down. So it would look the same, except it'd be reflected about the x-axis. Now, what if I have f of negative x? Well, if I'm changing the sign just on the x, you need to think about that. If you have a positive x value here and you change it to a negative x, all you're doing is reflecting about the y-axis in that scenario. So it's, again, it's the opposite of what people think. They're like, okay, if I change the sign on x, would that flip it about the x-axis? No, flips it about the y-axis, because if you're taking a positive x and making it a negative x, you're reflecting about the y-axis. Please think about in the previous problem, now I've already said what the graph of the negative root of x would look like. It would look like a square root function down here. What if I said the square root of a negative x? You'd say, okay, that's just going to take this graph and reflect it about the y-axis because it's only going to be defined for negative values of x. If I said, well, what is the square root of negative 4? You'd say, well, man, John, that's just the square root of 4, which is 2. Right. So at negative 4, you'd have the ordered pair negative 4, negative 2 if your function was the square root of negative x. It'd just be a reflection about the y-axis. Now, let's see that with a cube root of x graph. If I say, well, if f of x is equal to the cube root of x, and that cube root of x is my original blue graph here, it's going through like this, and the cube root, the points I usually like to use to define it are 0, 0, 8, 2, and negative 8, negative 2. The cube root of negative 8 is also negative 2. But then I'm saying, okay, what would the cube root of negative x look like? And I can say, okay, anytime I have a negative only in front of the x term, all that's going to do is it's going to be a reflection about the y. Oh, this has a mistake here. Boo! Boo! oh, I will correct that. Bad, bad, bad. That is not right. It says the graph will reflect about the x-axis. It's supposed to be a reflection about the y-axis. Now, in this case, is it wrong that I put x-axis? No, because the original function is symmetric with respect to the origin. So I was fortunate in that it's not going to matter. But I don't want you making the mistake and saying, oh, if he's changing the sign on x, does it reflect about the x-axis? No, not usually. This is a reflection about the y-axis. So I would say, okay, then this point 8, 2 is going to become the point -8, -2. The point that I had over here, -8, -2, gets reflected over the y-axis and becomes the point 8, -2. So please, it's not a reflection about the x-axis. I mean, it is simply because this is a function is symmetric to the origin. If I would have shifted it up or down, though, and then did that reflection, this would be very, very wrong. So it's just coincidental that it's also symmetric with respect to the x-axis, and you can reflect it. But anytime you change the sign on x, I'll go back to here, it's correct here. If you change the sign on x, it's supposed to be a reflection about the y-axis. Technically, this isn't wrong just because of the function I was dealing with. Now, if I wanted to vertically stretch and shrink graphs, then this one's pretty straightforward. It makes sense. If you have a function and you multiply it by some constant, well, as long as that constant's greater than 1, it's going to be vertically stretched by that factor. So if I say, what's the difference in the graph of f of x and 5 times f of x? Well, 5 times f of x vertically stretches all the y values by a factor of 5, just multiplies all the y by 5. Well, what if you have some constant factor between 0 and 1 that you're multiplying it? And you can say, well, then it's going to be vertically shrunk by that factor. So if I took a 1/3 times f of x, all of the f of x values are going to be 1/3 the height of the previous height. Now, in order to see that in this problem, I took a graph of the absolute value of x, the blue graph, and then I said, well, what's going to happen if I multiply all those absolute value of x by 2? And I said, well, all right, that's no big deal. I know the original graph would have the point 2, 2. When I stretch that, I'm multiplying the y values by 2, and I'm now going to have the point 2, 4. The point 4, 4 would become the point 4, 8 on the stretched out graph. You're just taking all of the y values and you're multiplying them by 2. That's vertically stretched by a factor of 2. Now, if I want to horizontally stretch or shrink a graph, and again, I need you to remember, anytime something is in with the x, it does the opposite of what you would think. So we just talked about vertically stretching. And I said, if you have a large number on the outside, it's going to vertically stretch it. If you have a small number on the outside, it's going to vertically shrink it. And that small number meaning a number less than 1. It's the exact opposite of that now. If I want to horizontally stretch a graph, I actually have to multiply the x value by a number less than 1 on the inside, some number between 0 and 1. And again, that's what I'm saying. Anytime something is in with the x inside of what's happening in the function, whether it's a square root, a square, a cube root, a cube, an absolute value, anytime something is in with the x, it's doing the opposite of what you would think. So here you think, oh, well, you're going to multiply all of your x values by c. No, you're not. You're going to divide them by c. And so if c is some small number, well, then it's actually going to be horizontally stretched by that factor of c. Now, if c is a large number, then you're dividing x by that large number, and it's going to horizontally shrink your graph. It's going to look like you're squashing it from the sides. So large numbers horizontally shrink, small numbers horizontally stretch. Let's see that in action. Here's an example. I have the graph y equals x squared. That's my base graph. And then I can say, well, all right, my base graph is my blue graph. F of x is y equals x squared. We know it contains 0, 0, 2, 4. It would contain 3, 9, -2, 4, -3, 9, and so forth. Now, if I wanted to show that the graph of g of x is equal to the group 1/2 x quantity squared, then I can say, okay, what am I supposed to know? I'm supposed to know that that 1/2 x, how would I get to that? Well, you're going to take each of your x values in your problem and you're going to divide them by 1/2. So you say, well, dividing by 1/2 is the same thing as multiplying by 2. Absolutely. So you're horizontally stretching this by a factor of 2. You take this x value, you divide it by 1/2. In other words, multiply it by 2. It goes out to the ordered pair 4, 4. What about the ordered pair negative 2, 4? Well, you take that x value of negative 2, you divide it by 1/2. Negative 2 divided by 1/2. That's the same thing as negative 2 times 2. You're at negative 4, 4. Now, please notice you could also just plug these points in and say, well, yeah, of course, that's going to work. Why is it going to work? Because now at x equals 4, if you plug an x value of 4 in there, you'd say, well, now I have to say 1/2 times 4 before I can square it. 1/2 times 4 is 2. 2 squared gives me the 4 back. So I know that this 1/2 in there, it's not saying to multiply all of your x values by 1/2, but to divide them all by 1/2. Please, again, remember, anytime you're working a problem and you're just saying, well, how am I supposed to know what's happening in it? If it's inside with the x, it's doing the opposite of what you would think. So whenever you're looking at something like this, I get so many students that say, oh, that's going to be horizontally shrunk by a factor of 1/2. No, it's horizontally stretched by a factor of 2, because it's always the opposite of what you would think when it's in with the x term like that. Now, if I want to have fun with one and just do a whole bunch of things at the same time, no problem. Please do remember, though, the first thing that you're always going to have to do is any horizontal shift, and then it doesn't matter the order of any stretching or reflections, but then the very last thing you do is the vertical shift. So if I were thinking about how to graph negative 1/2 times the group x plus 1 quantity squared minus 2, I'd say, well, your base graph is just your function y equals x squared. Now, what's the first thing you do? You'd say, well, the plus 1, that's going to shift it to the left 1 unit. So I'd say, well, I'd have this parabola shifted to the left 1 unit. It'd be y equals x plus 1 quantity squared. It'd be a parabola shifted 1 unit to the left. Now, what's next? The next thing I did is I dealt with that 1/2 out in front of the group. I can say, well, what is that 1/2 times the group x plus 1 squared going to do? It's just going to vertically compress it by a factor of 1/2. So it's going to take each of those y values and multiply them by 1/2. When I vertically compress it, you can also think about it as being horizontally expanded. It really is. So I can say, well, if I flatten all of the y values, it's going to appear more squatty as I go in. So now it's multiplied by a factor of 1/2, shifted to the left 1 still. Excuse me. And then that negative out in front, well, what does that do? Reflects it about the x-axis. So I can say, well, that's just going to take any positive y values that I've multiplied by 1/2 and now make them negative. So my parabola would be shifted 1 unit to the left, going up less, and now reflected downward. So I'd have my parabola starting point at -1, 0, and then moving downward. Then what? Well, it's going to go from that starting point of -1, 0 going downward. My very last step would be to shift 2 units down. I can say, so then the ordered pair -1, 0 becomes the ordered pair -1, -2. And that would be the vertex of this parabola, -1, -2. I should have labeled that point as the starting point of that parabola, and then I could draw it going down. And its y values go down at exactly 1/2 the rate of which the y values of this function go up. All right, guys, that finishes the PowerPoint presentation for this section. I did work plenty of plenty of problems in the homework assignment of me transforming functions. They break up the homework into certain sets, like wherever you're transforming the cube root graph, the absolute value graph, the parabola, x squared graph, and then they have you do a bunch of different transformations, starting with basic transformations, working towards a gorgeous combination of a whole bunch of transformations by the time you get done with the problem. Please make sure you see where I got my answers, and if you don't see it, let me know how I can help, and I'll be glad to do it.